Okay, I understand that many of you are a little bit lost with respect to these pictures of what we in distributed computing called protocol complex. So I'll come back to it, but a little bit after I covered the some more cute stuff, not that will give us some more interesting homework. So, what is the cute stuff? Let me we have a lot of people here that deal with shared memory. We have a lot of people here that not a lot, few people here which are professors in shared memory. So this question is opened to everybody, just to show you that if you abstract enough, we do not understand, until we think of it, we do not understand even what shared memory is. So I said that my model of messages, and in each round you lose one message, is equivalent. You can emulate shared memory and vice versa, and round by round. So if I take one night, what I call one round of my model, okay? In this round, I can present it as a problem in distributed computing. And the problem in distributed computing is each processor at the beginning, it's its own ID. And at the end of a round, it output some set of IDs. Okay? And I'm asking, what are the in my model, I want to present in my model, how do I specify that the story that I tell you, that I have an adversary that on each communication line takes at least one message. So it takes at least one message, may not be. It leaves a graph afterwards behind it. Can you specify what is this graph? What are the properties of that is common to all the graph that it leaves, so that if you give me some graph, I'll say, no, this is not a graph which is good for my model. What is the property that the graph left by the adversary that picks a message, that may pick a message from each connection? What is the property of the graph that is left? Anybody? Yes?
It should be connected.
What?
Connected graph.
Connected graph. Well, let me ask you, let us take 4 processors. Is this a valid graph that can be created after a round of my model? Remember, we have an adversary. There are 2 messages going in anti-parallel direction between every 2 processors, and he is allowed to pick at most one. So this is not good, because over here on this connection, you remove the 2 messages. So this is not possible graph left by my adversary, right? So what is the property of the graph left by my adversary? The definition, yeah, go ahead. What? Direct connected? Direct what? Of course, it's a directed graph if I am allowed to put anti-parallel. But what's the property of this graph? It's not every graph. What is the property? How do you say there is connection, there is in each anti-parallel, you can pick one. What is left? What? Who said, I heard the right word? Two.
Fully connected graph. That was
What?
Fully connected.
No. I don't know what is fully directed. Okay. This is the name in mathematics. So anybody wants to answer? What was the answer there? Tournament, yeah, beautiful. So the word tournament was not used here in the previous session in the right precise mathematical term. What you saw, the tree for mutual exclusion is not a tournament. A tournament in mathematics is what we think of a tournament. We have n players, and they all play each other. And there is no draw. All of them either win or lose. In each match, there is win or lose. Okay? And those of you that took algorithms, no problems of scheduling this god and stuff like this. My adversary leaves behind a graph which is a tournament or a superset of a tournament. You can add now to the tournament any other parallel edges that you want. Okay? So now we all understand. We can pose my model as a task, which says you return names. What are the properties of the sets of names that you return? Well, the combination. The combination has to contain a tournament. Okay? Let me ask you, if you understand what is shared memory, let me ask you the following experiment. We have a shared memory, n processors. Each one has a cell. At the beginning, all the cells are bottom. And the process is, each processor will write its name in its cell, which means it will put something in each cell which is not a bottom, and then read all other cells in some order. I don't care about the order. It will read in some order, and will return the names, the IDs of all the processors that it saw wrote in their cells, right? So it's the same story. We have some process by which processor returns IDs and processor return IDs. Okay? And I ask you, if you understand shared memory, what is the properties of these sets? Is the properties of these sets it's enough to say, is it? This will specify, in other words, there is no more properties than a tournament, because obviously, if there are two processors, we understand shared memory. If there are two processors and they both write and then read, at least one of them must read the other. So the set returned in shared memory is at least contains a tournament. But is this shared memory? This is shared memory? Or shared memory has more properties than my adversary? Because if it has more properties than my adversary, I have to show you that my adversary can implement these properties of the shared memory. You all know what is shared memory? What are the properties of shared memory? Or show me, is there a property of shared memory that my adversary does not possess in one round? it's a tough question. This one, you do not need to be ashamed if no answer. Yes. What?
In shared memory, we're sure that everyone sees everyone's answer in one step, in one round.
We are talking about the process. What is modeling? Modeling is taking some story or...
As a graph, it must be
I'm talking
directed
about a
and
processor. Each processor writes its cell, and then in some order read all other cells and return all the cells in which it read no bottom. And so each processor returned a set. What are the properties of this set? We just argued that shared memory is stronger than my adversary. But really, strictly stronger will mean that the graph that it leaves behind contain another property that my set of graphs do not contain. Can you find the property that shared memory has that my doesn't? And then I will ask you therefore, so what is shared memory? And I want to tell you, because I asked this question myself 30 years after I knew what is shared memory. I don't expect. It's as I said in the abstract, it's about asking the question. Nobody ask yourself, what is shared memory? Yes, over there is a question.
If I understood you correctly, the special property which shared memory does have is that if one process had seen some set of non-bottoms and the other process had seen that the first process has written its value, then it is a kind of transitivity. The second process will see at least those set of non-bottoms.
Can you translate, Peter? You will excuse me, but you know, I am half deaf. You cannot translate. Well,
so the set of outputs of different processes, it doesn't matter if I'm close to you or more far away. So the set of IDs returned by different processes should be related, I guess, by containment. That's what you mean.
Don't change the problem. You return IDs. No tricks. No. It's
well, you write your IG. You write your IG. You read the IDs of the others.
Yeah.
And the set of IDs you see should be either a subset of the IGs seen by the other process or superset.
No, it's not correct. This is what you said is called snapshot. Okay, it's not correct. This was a big result in distributed computing and in shared memory. By doing iteration, you can return snapshot, but shared memory does not return, as I outlined it, that you read in some order, does not return snapshot. And if you want, I will put an example on the board. Okay. Anybody else? Sure? Peter, you have a volunteer here.
Well, maybe all sets should be the same. All sets had written by...
How it can be the same? Take two processors. I write, and then I read only myself because the other one didn't write. The other one writes and reads, so he reads himself and reads the other one. We do not return. Two processors return snapshots. That's correct what he said about two processors. But three processors do not return snapshots. We have a... And let's say this is the last one.
Yes, I can guess two ideas. First, similar to databases, like optimistic looking. So we are guaranteed that writing is always finished and correct, but reading is should be verified by readers after some time. So it's not snapshot. You necessarily reader necessary itself to verify result. And second approach, like in
I don't look for
Ethernet.
approach, I look for an answer. No approach, I want an answer.
Maybe like second, maybe like Ethernet systems, you write and immediately read to understand that your memory place is not replaced by someone else.
Can you translate?
No, I don't think it's. I'm sorry. I don't think it's related.
Okay, let me tell you what is the simple property that my adversary does not contain. It's shared memory. Think about the processor that wrote first. Shared memory, our understanding of shared memory, execution, is a line. The first atomic step is of some processor writing. All processors will return its ID, which means there will be one ID common to all sets. I claim my adversary doesn't have it. Why there is it's a tournament. Why should there be somebody that will lose or win everybody? Not necessarily so. Okay? So shared memory has more properties. So we need to add the property that is a tournament which contains, let's call it, because I'll go, a strict king. A strict king means everybody is, because I'll talk in a minute about semi-king. Somebody who everybody looks at. And the question is, oh, we found something that shared memory has that the adversary doesn't, my adversary doesn't have. And the question is, perhaps we can find another property that shared memory has that my adversary doesn't have. And the answer is no. This is the only property, and we can stop here. Okay? So let me convince you. No, we can leave it as a homework, but okay. So this leads to the question, we now know that we have a graph in which at least one is returned by all. Okay? But let's take this one that is returned by all. Okay? If we take this one that is returned by all, I can repeat my argument with respect to the second value that was written. Because the second value that was written will be now seen by n-1 processor, at least. Maybe it will be seen by n. It will be seen by n-1. Okay? It will be seen by n-1. So perhaps leave it as a homework because we don't want to dwell on it too much. Homework. Prove shared memory if and only if it contains a transitive tournament. What is a transitive tournament? If I beat you and you beat him, I beat him too. Okay? This is a result that I didn't know until a few days ago, because I called this result in another name. I called this result, I knew this result, but I called this result shared memory is fat immediate snapshot. What is fat immediate snapshot? Take immediate snapshot structure and add to it stuff. You don't know what is immediate snapshot, and it doesn't matter. But just to show you that our level of understanding, because I then talked to somebody and I said, so suppose that the return is immediate snapshot, and you say, oh, you mean that it's transitive. So in some way, there is something interesting going on here, that this message adversary transform all sorts of things we thought before into graph theoretical terms that of transitivity. So let me give you now the real problem, which is for some of you that really want to spend time, it's instructive. I want to say 2 iterations of my adversary will give you shared memory. What is the meaning of it? Tournament, as our savior over there, Nir Ashur over there, told us, tournament is between every 2 nodes, there is at least one directed edge. Do this as a homework in algorithm. Says in a tournament, there is a node that either directly or in 2 steps is reachable from all. And this is called the king of the tournament. Okay, so every tournament has a king. But we want a strict king. So I know that if the adversary will give me a tournament and then will give me again the same tournament, I will have a king. And king is somebody that everybody read. Okay, but if everybody read him, then I'll have a shared memory. Then believe me that this is shared memory. But no, the adversary can give me in the next round another tournament. Prove that in 2 rounds you have a strict tournament, transitive tournament. You have the system contains a transitive tournament. Everybody understand the question? No. Okay.
Can you please plot this as an image, as a graph?
So we have this. You see here, for example, every node has an outgoing edge. So if I do this, arbitrary, and if I add more, I have a tournament, right? Here I have a tournament. Now, in a tournament that everybody has outgoing edge, nobody return all the rest, right? Because the guy that you have an edge to, you didn't return him, okay? So a strict tournament is now. If you now take and say, okay, let's think of this and as an edge as sending a message, okay? Now, we think next round. Next round, what you send to the other guy is, you don't need to send your name because what you send to the other guy is what you heard already by now. Okay? So, if the adversary will give you the same tournament, then in the second round, you heard from somebody behind you. So you will pass his name to this king. So if we know there is a king, the king in 2 rounds will hear from everybody 2 away from him. Or her, the queen. Okay? So after 2 rounds, if the adversary will stay with the same tournament, I will have a shared memory. But I want more than this. The adversary can be with an adversary. The adversary will give you another tournament. Can he prevent you from having shared memory in 2 rounds? And this is not a research question, this is a puzzle. The answer is surprisingly yes. No matter what are they, if you take 2 tournaments, and you take 1 tournament, and in the first tournament send messages, so everybody hears of something. Then you take another tournament. In the second tournament, everybody passes its name and what it has heard already. Everybody that you know about. Okay? Then you'll have a shared memory. Okay, and now this is very interesting result, that the minimum, when shared memory returns to you something, the something leanest that it can give you, it always contains what is called this transitive tournament, which we call immediate snapshot, which is a known result, but now you see a graph theoretic. So we still have, so let me now, let's switch to this, so let me just to make some more few games. I said that using Sperner, that if I have an adversary that can remove a message on each connection, can remove a message on all the n-choose-2 connections, I have a shared memory. And shared memory I cannot do, this is the result, I cannot do any set consensus. There is no avoiding that each processor essentially will return itself if I do election. So you cannot do set election in shared memory, in this model. So suppose that I said, you know, adversary, you can temper and remove message from all connection, aside from one connection. You can choose, for in each round, one connection back and forth you are not allowed to touch, to remove a message from. And now I ask, is it still correct that I cannot do any set consensus? In other words, it's strict. If I disallow him from round to round, not the same man, not the same connection, but in each round, you can remove on any of the n-choose-2, but one of them, of your choice, you are not allowed to touch. Will it force, so what it mean that the programmer now can write a program that will return, that processor will solve n-1 set consensus? And the answer is yes. If the answer is yes, then the question is, so what is the quantizing of these numbers so that I will have n-2 consensus, n-3 consensus? And this will be, hopefully, in an upcoming paper. This is shown. It's one simple generalization. So you will get the idea just from this, just from this example. So for this example, we have to do another step. And the step was we didn't get names. The step was that somebody incorrectly, but almost correctly said that shared memory return sets which are related by containment. And my question is, now I know that my adversary can implement shared memory, but I don't need it, but my adversary can implement shared memory. I need it, okay. My adversary can implement shared memory. Can somebody give a simple algorithm that now will be some iteration of shared memory that will return, that each processor will return sets, and all the sets are related by containment to each other? This is a tough problem. But turns out that the algorithm is so simple that if you thought in this direction, you will see it. What is the direction that I say it's simple? All of you are computer science, so all of you have studied algorithms. But in my opinion, probably nobody agrees with me, but in my opinion, didn't study for the right book of algorithms. To me, the right book of algorithms is by an author called Udi Manber, who wanted a very good theoretician that wanted to be practical, and now is a big practical. He's I think he's still the vice president of search for Google. He wrote a book, Udi Manber wrote a book, and the idea of the book is, let's try to do every algorithm by recursion, because mathematics tells us that the only solvable problem are problems that are called, languages that are called recursively enumerable. And this is a different name for recursion. So if you try to come up with an algorithm, it always has a recursive version. I didn't prove it yet, but I'm sure that it's the same true for distributed algorithm. But you have to be more careful in defining what is recursion and things like that. So let me give you an algorithm, a recursive algorithm that will solve this problem, and you all will agree that this is recursion. And this is not a new thing. Sergio Rajman and I wrote a paper, Recursion in Distributed Algorithms. So this is an algorithm from there, not invented there, but notice that this is a recursion. What is the recursion? The recursion has a parameter that goes down. So the recursion is do a round of shared memory. In this round of shared, the recursion now is parameter n. Now take shared memory and each processor do what we said now. Write his name and read. Okay, we just said the value that was written first has to be, no, this is not interesting. What is more interesting is that it has, but this is a consequence of what I just said, that at least one processor has to return all the IDs of everybody. Because think of the last write. The processor writes and reads, right? So the last processor to read must return all the writes. So at least, not necessarily one, at least one processor will return everybody. So there may be few processors that have everybody. All these processors will return the set of everybody. Okay? And then I have to continue the recursion. What is the recursion? All these processors return, they are not there anymore. The rest of the processor call the version of this problem with n-1. What is the meaning of this version of n-1? It's write and read, and if you return n-1, return the set, and that's it, you are done. If not, go to n-2, go to n-3. This is a recursion. It's not the same memory, it's a different memory. Remember, I always talk about memory, so I didn't make it clear. I am in the model of messages. I just say 2 messages are shared memory. But my model continues to be a model of, you don't see what happened. When you do the n-1, you don't see the memory of the n. It's a new thing. You get a fresh memory, all of it bottom, and you write and you read. Only that now we have at most n-1 processors, because at least one was stuck at level at the nth call. Maybe more. If more, then nobody will read n-1 in the next call, and they will all go to n-2. Right? And we'll continue. So now I say, to prove to you that the returns are what is called snapshot, they related by containment, is trivial, because those that return at level n, they return the whole thing. So everything that will later be returned is a subset of it, right? Is related by subset. Now just continue, this property holds, okay? So we can produce snapshots. So let me now convince you that I can do, if the adversary cannot one of the connection of each choice, it is not allowed to tamper with in a round, then it loses, and the programmer can force n-1 consensus. How? Let's do first this snapshot by using 2 rounds. Each round we have a shared memory. Using n time the shared memory, I now produce snapshots, right? Okay. After I produce snapshots, I take one single round of my adversary, and I tell everybody, just tell the other guy what is your snapshot. Okay? So I will have 2 guys, because one connection is not tampered with, I will have 2 guys exchanging their snapshots. And my rule will be, okay, after this round, if you have heard another snapshot, and this snapshot is larger than your snapshot, take it. I claim I now cannot return n snapshot. Without doing this, I just did give you an algorithm for a snapshot. It doesn't preclude that all the snapshot will be different. Now, using just single round, where the adversary is constrained, I can force the number of snapshots that returned to be at most n-1, because somebody will choose somebody else's snapshot, and it's all the time in the same direction, so one snapshot will be lost, will not be returned. And now the set consensus algorithm is, okay, after all this, you have a snapshot, return the maximum ID in this snapshot. At most n-1 IDs. Everybody more or less? Okay. So now you can say, okay, the programmer, but will not go there. It's simple, but the programmer can force n-1, but perhaps it can force something better even, n-2 set consensus. No, that's where it ends. It can force n-1. In order to move to 2 set consensus, I have to preclude the adversary from another n-1 connections. Only then I will be able, I think n-1, I don't remember the number. So this is how many specify the consensus power, the consensus power of adversary according to the number of connections that it can tamper with. So this leads us to, this opens a whole, which I didn't do yet, because once a whole viewing all of distributed computing, not through process failure, but through connection failure. Because connection failure is more general than process failure. I can model process failure as a connection. Not only this, it makes things simple, because suddenly I say, processors never fail. It's the connections that fails. Okay? So there was a big, great mind dealt with a question about consensus. What happens with a processor that fails? I don't know. I don't know whatever they mean fails. What happens with a processor that fails? Is the algorithm okay if the processor that outputs something not in agreement with others later fails? Should we call it consensus or not? What I want to show you only, that when you have the wrong notions, you ask the wrong questions. This is, think of it. Processors never fail. So these questions makes no meaning. This is, excuse me for the comparison, is like the alchemist, arguing about which is faulty definitions. So let me now go back, and because really I understand that some of you, this is the first time sort of to see theory aspect of distributed computing. So there was a very important notion, this what we call now, the name is protocol complex. So let me go back to protocol complex and repeat it, and if you take this abstract notion out of this talk, I've done my job. So let me go back to it. So essentially, I'm repeating. I will come to this one, but before, let's go back to this. Okay, and let me explain again. What is this slide about? Again, this slide is, I want first to prove that in the model in which I have the two red armies left and right, and one night they send messages to each other. If the messages were non-faulty, then they can have a rule. One of them says they know that they will both get the same view at the end of the round because they both will get the same messages, okay? And getting the same messages, if the messages disagree, they can have a priori rule that says messages disagree, choose the less risky option. And let's say the less risky option is retreat. Okay, but if you are general and want to get the next, it's the opposite. You don't care about life; you care about the number of stars that you have on your shoulders. So whatever, there is a rule. Okay, but now we put some uncertainty about what will be their view in the morning, because they don't know they know that one messenger can be taken over, but maybe not. And they don't know if a messenger is taking over, will it be the messengers from left to right or the messengers from right to left? Right? So there are three things that can happen in the world at the night. No messengers will be taken. Messengers from left to right will be taken. Messengers from right to left will be taken. Right? And I say, okay, I don't know. One of them will happen. Let's take now the situation, the views of processors in each of these scenario of what happened. Okay? And in this picture, oh, here it is. We moved words. This is a test of your of my what do you call it? Color visibility. Okay. You see, this is the view of two processors in the case that the message from left didn't reach right, but the message from right reached left. Okay, this is the world. This is this world. Okay, so this view, this state of processor. Okay, perhaps we will switch. We have message left to right, ambushed, taken. So let's do it pictorially. This message was taken. This message came. So this is the guy who is on the right, what I call the right army, the side right. This is the right. So what is his view? I didn't receive any message. No message. Right? This guy, which I call left, he said, I received a message. Right? Okay. There is another situation of the world. The other situation of the world is that the two messages went through. The ambush did not succeed. Okay? Then I get the guy on the left. He said, both of them got the message, right? So he received the message. The right guy says, I don't write it here because he said no M, and this is received the message, no received. No received. No R. Okay, so this is the situation of the world. They both received. Right? And the last situation of the world is the reverse of this. This is left. Let's put it here. Left, right? This is the message to here was cut, and the message to here succeeded. So this right said, I received the message. The left army says, not received the message. Okay? Everybody understand this picture? Yeah. Anybody question about this picture of three pairs? What? The middle pair. Why did I switch? Because we'll see in a minute, but it's the same thing. The middle pair is commutative. Okay? I intentionally wrote it this way. Why? Because now I have three situations of the world. But there are some nodes that cannot distinguish, did this situation happen or this situation happen? You see, in here, when I take the left, I did not receive a message. Then look at all the other situations. He received a message. So he can distinguish and say, this world has happened. The other guy received a message and I did not receive a message. It's not only that he knows what happened with him. He knows what happened with the other guy. Because if always you'll know what happened to the other guy, we will be able to do consensus. So this guy knows that this happened. This guy knows that this happened. But here, this left. These two are indistinguishable for it. It doesn't know whether the world was this or this. It doesn't know about the message that it sent, whether this message was taken or not. Here, this guy also does. It knows that his message was not taken because this message was taken. So these two situations, right in this world and right in this world, see the same thing. And the right in this world and the right in this world see the same thing. And now when you write an algorithm, you, after one night, you have to assign a value to each node. What do you output, right? So in this one, the right, I don't remember what it said. Let's call it, I cannot call it R because I used R for received. Let's call it retreat. But retreat starts with an R2. So let's call it a coward. And let's call this a hero. Okay? In this world, this guy is forced to output coward. Because we need agreement, it means that this guy is also forced to output coward. In here, this guy says hero. So this guy, because he's the same situation of the world, and if they want to attack, they need to attack, then he's also has to output age. Okay, so what we are left with is this thing in the middle, right? But this thing in the middle is now a problem, because here you output C. And here, this guy doesn't know, am I here or am I here? So he's forced to a C also, because it's the same view. It's the same local state. And here, this guy, it's the same, it's a copy of the same picture. It's the same local state. So here, if we satisfy this, here it will be a C, and here it will be an age. Contradiction in the situation of the world in which the messages go through. And this is the easiest situation. We output different things. So what was on the slide is, because these two are the same, I combine them. It's the same. Why should I draw it as three separate things? If I have two situations in which I have a processor that has the same view in the two situations, put it as a single node. And then I can explain better where this contradiction comes from. Because when you glue together two views of the same processor, which are the same, and you get a path, then this is the problem. Because one side of the path has to have one value, one side of the path has to have another value, and no matter what you'll do, what your algorithm will do, it will be forced to have the same edge as one edge having one value on one side, one value on another side. The two processors cannot agree. Okay, so two processors cannot solve consensus. For two processors, not solving consensus is for two processors not solving set consensus, because the only subset of two is one. Okay, so the question remains valid of, now we have three processors. Okay, perhaps three processors can do n-1 set consensus, where n-1 now is not consensus. n-1 for 3 is 2 set consensus. And the answer is no. If you do this gluing and now you understand this logic, the answer is no. And let me now go to where we stopped, where we were, that the answer is no. Back to the okay. So what we'll do here, and now no, don't switch. Everybody sees this. Let's keep this on over there. What I'm saying here, I am comparing, I am identifying. I'm not identifying. I'm taking two models. One of them is my adversary, and my adversary sitting here. The network is a complete graph of three processors, which is a triangle. Okay, and the adversary sit on these three connections. It can disable one messages from each of them in a round. Okay, and I want to equate it to say now time division. Okay, in this one, everybody sends to everybody in a single round, and I say no. We now stagger this. In round 1, 1 sends to 2, and 3 is quiet. In round 2, so I say, in round 1, this will be the communication. 1, 2, and I have to look. 1, 2, who is quiet in the second round? 2, I think. Okay. 1, 2, 2 is quiet, which means at the second round, I will use this connection, and the third round, I will use this connection. So I just do from round to round connections of pairs of processor. And these pairs of processor, the adversary can come and plug a message. And I say, let's not get into it, it's a very simple to see that essentially these things implement each other. Because if I have the adversary going from every time with the 3 of them, I can say, hey guys, just ignore what. If I say in each round just the 2 of them, I say, okay, you in the first connection, you learned something. Don't forward it in the next round. Just imitate it for the 3 rounds. Behave as you were behaving in the first, like you're in the first round. So the 2 are equivalent. So I go with the model of equivalent to my adversary, in which each time 1 we schedule 1, 2, time 2 we scheduled 1, 3, 1, 3, and time 3 we scheduled 2, 3. And let's see how these pairs of the, what is happening here. So we get this picture. Let me go now. We get this picture. What is this picture? I say, what is this picture? It's gone away. Okay, let me do it here. Let me do it. It's the same. We have, it's called the delay. Okay. Remember, I took this and I made it into this because I glued these 2, glue. I glued these 2 and I glued these 2, so I made it into this, right? So in the first round now of 3 processor, when I look at the world at the morning of the first night, processor 3, we know ahead of it has no possibilities of changing its worldview, and it knows it. He does not send messages and he does not receive messages. But processor 1 and 2 can change their view, right? So I get now a combination of 3 combination of views. But it's the same combination that we had before, only that I had processor 3 that doesn't change. It's the same thing. This picture, this thing is this thing. Right? It's what processor 1 and 2 says in the morning of, and processor 3 sits there and says, nothing changed for me. Okay, so I get this situation from 1 and 2 with processor 3, this situation from 1 and 2 that no message was lost with processor 3, this situation for 1 and 2 with processor 3. So these are the 3 views of the world after the first night, right? Everybody understand this? Simple, okay. So what happens the second night? The second night, processors 2 and 3, 1 and 3, processors, no, 2 and 3. Oh, see, I missed that. 2 and 3, in the picture. I can do it whatever I want. Okay, I say processor, whatever we don't want to use, okay. Let me move it. This is the first one. And now, after the first night, I have this situation of the world. And I don't know which situation of what happened. Okay? So I say, what are all the possibilities? For each situation, we will have now exchange of messages between processor 2 and 3. So each edge 2, 3 here will become this path. And this is what's in the picture. You see this. This happened in the first round. What is this happened in the first round? Processor 1 didn't get a message. Processor 2 get a message. Processor 3 just sat there and say, nothing will happen to me now because the algorithm says no message was sent to me tonight and I don't send a message tonight. Okay. But now this happened and now we move to the next round. In the next round, processor 1 says, nothing will happen with me. In this round, I am quiet. I will not send a message and I will not receive a message. So what happens? 2 and 3 now exchange messages. If they exchange messages, they get, this is processor 3 says, I didn't get a message. This is processor 2 says, I did get a message. This is processor 3, I did get a message. This is processor 2 says, I did not get a message from processor 3. Right? So we get this subdivision of the edge. But processor 1 doesn't do anything, so we have, if this was the world after round 1, we have 3 worlds after the next round, coming up of this world. Okay? But no, suppose this world didn't happen, this world happened. But if this world happened, I say, then this will be the 3 worlds, because this edge is common to these 2 worlds. Okay, and then if this world happened, this edge will be subdivided. And therefore, I get these 3 worlds. So which means that after 2 rounds, I get 9 different worlds, right? And if I will continue in the next round, the processor that is quiet, processor who was quiet, let's see. In the first one, processor 3 was quiet. In the second one, processor 1 was quiet. So in the third round, processor 2 has to be quiet. So processor 2 has to be quiet, which means processor 1 and 3 will talk to each other. What will happen? Will be 9 worlds. And in this world, processor 1 and 2 talk to 1 and 3 talk to each other, which means this will be divided to 2. Which means now the worlds are 2. Doesn't participate, so just edges going to these 2. When I look at this edge is common to this world and this world. So this will be connected, this will be 3 worlds connected here. And here I have 1, 3, again, which one? We are now doing 1, 3. 1, 3 again, so this will be now divided into 2. And 2 will be, 2 is quiet, will be connected to them. And 2 quiet will be connected to them. Okay? And you get the idea by now, I hope. That now I will have, I had 9, I'll have 27. We encountered already. It's always go by this factor of 3. Okay, so now we are asking a similar question to what we asked at the beginning. And what we asked at the beginning with one line was, I have a value here and I have a value here, and we said if it's connected, it has to force an edge with 2 values. Okay? And this was something interesting to combinatorialists. And they said a generalization of a path with 2 colors at the end, and now putting the 2 colors in the meaning has to create an edge that one side is one color, one side is another color. Is it true now that I go instead of a path is, I won't call it a triangulated path, but it's pathed path, right? We took and we put edges in a path. What is a triangulated triangle? We take a triangle and we start triangulating it, putting now not nodes in the middle, but now putting edges from in the middle. Okay, so this is a triangulated triangle. And they ask themselves, so what is the generalization of the one line having one color here and the other node has color here? Here it will go farther. It will have in each corner different colors. So call it the color 1, 2, 3. Okay? So in each corner, different color. But as we understand it, in distributed computing, if you look at these views here, these are all the views that corresponds to processor 1 and 2 communicating between themselves, but never hearing any message, none of them, hearing message from processor 3. In this case, these processors are not allowed to output 3 because I said for them, processor 3 is not participating. Okay? So if we are going to solve the problem, we are going to give colors to this side, which is from the collection of 1 and 2. Similarly, over here, we are going to give from the collection of 2 or 3. And over here, we are going to give the collection of 1 and 3. Okay? So this is now called the Sperner coloring. And I just keep it for triangulated triangle, but it has the obvious equivalent to higher dimension. Instead of talking about triangulated triangle, I can take a tetrahedron and tetrahedra it, okay? And mathematicians has a name for it. It's a subdivided simplex. A simplex is any generalization of the Gaza pyramid, okay? It's a line, it's a triangle, it's a tetrahedron, it's any complete, think of it as a complete graph among n. And now you take the complete graph and you subdivide it to other complete graphs inside in a fashion that I did here, that you cannot just plant it arbitrary, but okay. And then they asked, now that I need to color it, is it true that in the line, I'm forced to color an edge by the two sides by 2 different colors? Now I will be forced to color a triangle by 3 different colors. And the association that we make is that an algorithm is only a coloring. What does that algorithm do? At the end, it takes a local state of a processor and maps it into an output. So an algorithm is some coloring. So if the mathematician told us that you must now create a triangle that will have the 3 colors, then we cannot solve two-set consensus because we'll have a triangle, and a triangle is a real morning in the world after you stopped. And in the real morning of the world after you stopped, each of the 3 armies output a different result, output a different leader. Okay? So that you don't think that this triangle, that the existence of this triangle, which has to have 3 colors, is such a deep, the derivation of this is such a deep result. No, in a sense, it's a trivial result. And let me show you the proof of it. If you go over algorithm with line by line, we can do even a proof here. Let me prove to you a Sperner lemma. Okay? What is the proof of a Sperner lemma? Let's have this triangle. Here is the way that distributed guys, classical subdivided simplex of distributed guys. Okay, so here we have processor 1, 2, and 3. And here we are allowed to do 1, 2, here we are allowed to do 2, 3, and here we are allowed to do 1, 3. And the question is, are we forced to create a triangle, any coloring that we do, are we forced to create a triangle over here? And as a combinatorialist or graph, we will now define a new graph. What? The dual of this graph. No, it's not the dual exactly. No, a node outside. And in each triangle, I put a node in the middle. Okay, so all these nodes that I added, all these dots that I added are nodes in a graph. When do I connect these two nodes in this graph? Okay, when the edge between them crosses an edge of from the coloring that you did, that it's colored 0, that it's colored 1, 2. If you have an edge, now you'll do some coloring on the boundaries, but under restriction, and then coloring. If you have an edge 1, 2, and you have a node here and a node here, and you connect them, if you can connect them through an edge 1, 2. Otherwise, you do not connect them. Everybody understand what is the graph that I'm going to do now? Okay, so let's see. Suppose that I have the coloring of 1, 1, 1, 2. Then I claim this is the edge outside. I can have an edge here. I will not have an edge going here and going here because it crosses one edge. So I'll have an edge here. Now, maybe this is colored 1, so I will have an edge here. And if I have an edge here, I will have also an edge here. Okay? And depending, if this is now colored, no, I will not have an edge here. I don't mind, what did I say? I will have an edge here. Okay. But now, how is this colored? If it's colored 3, then I will be in bed because it's 1, 2, 3. So let's say this is colored 2. Then this is an edge 1, 2. I will have an edge here. Okay, so depending on the coloring of the nodes of the triangulated triangle, I now get a graph. Okay? Let me ask you. If I take a node, this I call node external, there is only one of it, and all the rest of the nodes I call internal. What is the possible degrees? What is the degree is the number of edges adjacent to a node. What is the possible degree of this internal node? Anybody? I cannot hear. I hear somebody saying something, but what are the possible degrees? Yeah.
We connect only nodes. The edge has 2 different colors.
Look, for example, we can have a triangle which has 1, 1, 1. And I claim the node in the middle will have degree 0. Because to connect to somebody, you have to pass through an edge 1, 2. Okay. So 0 is possible. Is 1 possible? Can you give me an example that an internal node has degree 1? Anybody? What? 1, 2, 3? These are the possibilities. How do you get 3? Okay, so let's do it because soon Peter will stand up and I want to finish this. So, look, if you have degree node 0, it means that one of the node is 1 and one of the node is 2, right? So you have this edge. But now let's look at this node. This is 1 and this is 2. Let's look at this node. If this node will be 3, we are done. Well, what we are talking about? I mean, we have a triangle 1, 2, 3, right? So we are working under the assumption that you can color the nodes of the triangulated triangle without fully coloring a triangle with the numbers 1, 2, 3, right? So the only possibility left for this node is to be, if it's 1, we'll get this edge. If it's 2, we'll get this edge. Conclusion. The only possibility of degrees of a node internal It's either 0 or 2. What is the name common to 0 and 2? I heard somebody, I don't know. Even. The degree of an internal node is even. Okay. What is the degree of this node? Well, no matter how you color, so Sperner lemma of the one dimension says, it doesn't say not only, it doesn't say if you have different colors on both sides of the path, not only you must create an edge that will be of different color, the number of edges like this will be odd. Why? Think of it as 0 is first floor and 1 is second floor. So each time that you switch from floor to floor, you go through an edge, either 2 to 1 or 1 to 2, right? So you start at 2, you go to 1, you go to 2, you go to 1, but if you start at 2, for each up, for each down, if you didn't stop yet, there is an up, down, up, and there is the last one, which means odd. So the degree of this node is odd, and the degree of all the other nodes is even, which contradicts what? Which contradicts what? What? Yeah, there is what's called there is a lemma for it, even but this lemma not somebody. It's called the Handshake Lemma. The Handshake Lemma says that if we take all the people in the world and they shook hands over their lifetime, and we ask them how many hands you shook, then if we add all these numbers together, we will get an even number. Why? Because every hand is shaken from both sides. Right? So the Handshake Lemma says that the sum of degrees of nodes is even. But here in this graph, the sum of degree of nodes is odd, because this one all counted even, because each one of them is even. This one is odd, and even plus odd is odd. Conclusion. It cannot be that you colored with 1 and 2 in the middle. You must have created an internal node with a degree 1. How did you create an internal node with a degree 1? By full coloring. This is the only possibility of degree 1. Simple. A very useful, amazing lemma with a proof, which is, and if you understood this, I think that this is a good time to stop, and perhaps if there are some questions, tend to the question, but not, and I thank you for being on TV there is the survival game, that you survived all these 3 hours, not...
So we do have time for questions, so please go ahead.
Why we assume round robin for 3 processes?
What? When we
round robin. Why?
Because this is a simple way to convince you that the pattern of communication create a subdivided simplex. Because the whole idea at the time, the whole big thing at the time, was somehow to create a subdivided simplex and to prove the impossibility of set consensus for read-write through the subdivided simplex. I said in 1990, Soma Chowdhury posed the question. And then she did something she should not have done, which I do many times too. If you have some idea, somebody tell you some idea where to go, don't divulge it to. She wrote in the paper that she published, she says, there is mathematician that was interested in distributed computing, Mike Sachs, and he says that he thinks that impossible and Sperner lemma is involved. Okay, so he started to work on this. But I read that Sperner lemma is involved, and some of you have been here in the 2 years ago school, and you'll see Hirli again, Hirli and Shavit, read that Sperner lemma is involved, and this is a big hint. Among researchers, all you need to say is a single word, and things are done. But it was not done. It took 3 years, and we all came somehow with a proof of the impossibility. Okay? It was Sachs and his student, and they used some point set topology. It was extremely complex to read. There was this Hirli and Shavit. They wrote, in my opinion, even a more complex and even with some mistake, but they didn't only prove set consensus impossible, but they show a gestalt. Every read-write contains some subdivided simplex, and you can solve a problem only if you can color a subdivided simplex. They not only proved impossibility, but did something. My student and I did just concentrated on this impossibility, but we did not get a subdivided simplex. If you notice, the only properties I used is the proof of Sperner lemma. And the proof of Sperner lemma will apply also if you have some surface, if you have a surface which is not, you cannot put it in the plane here. Think about, you take a tire of a car, and when we were kids, we would sit on an inflated tire and go in the ocean. Think about a tire of a car that you cut a triangle in it, and then you painted all the rest with triangles. Okay? In some way, for me, this will be a triangulated triangle because I don't use the fact that it is in the plane. I just use the fact that two triangles share a face. They share a face between them. I feel the whole thing that it shares a face, and I can do the argument, okay? So my argument will go through even for what is called, it has a name in topology called torus, for example, any surface. Because I could not get this, I knew there is a subdivided simplex, but I couldn't get it. Today, a few years and some decades later, it's trivial. It's trivial means that somebody who didn't see anything before can see and get convinced. So that's why I did it.
Well, it's trivial.
I mean, for people who know the past, this was wow.
Yeah, it is trivial, but there's something hidden here. The fact that this model is equivalent to read-write.
What?
So you didn't really show that this is equivalent to read-write. Of course, yeah. So you need to show this, but this is hidden somehow behind. Yeah,
so you see, because I got a surface, I could not say it equivalent to read-write. I didn't know that it's equivalent. It's a surface. I don't know what. So I just could prove no what do you call it? No set consensus, because this thing is also a surface. But I couldn't. So later, we could prove subdivided simplex, but it was still, you know, something called immediate snapshot and some argument. Who showed that immediate snapshot is something? No, it's trivial. Here is a subdivided simplex.